Hello, folks. Hopefully, if I play my cards right, I'll finish early. And hopefully, if I play my cards right, I'm not going to confuse you, except in one slide. So this is joint work with a few other people. Dario Fiore, Argenaro, and Emanuele Giunta. And hopefully, we're going to get Ioni print soon. We're going to get Ioni print soon. So the topic of this talk is new constructions for lookup arguments. So I hope some of you have seen lookup arguments before, but just as a refresher, there's a specific type of SNARK for a very specific type of relation. And the relation looks sort of like this. We have a table that's supposed to be even arbitrarily large, depending on the application. And then we have a commitment at the table. Actually, the verifier can hold it. So it's done a processing time once and forever. And then sometimes I want to prove that a certain set of values is in the table. This is actually a multi-set. Here it says a set, but I mean, there could be repeated instances inside F. All right, and that's my proof PyLookup. So I give two commitments. One is a preprocessing time, one is a proving time, and that's what we get. Now, lookup arguments are pretty useful because for several applications. So to some extent, they abstract something that's close to batch membership proof. So if you have a set of users, think of permission lists or block lists, and you want to prove that a subset of the users is in that list or not, you can use lookup arguments. But also, they're really interesting, usually because they get us faster SNARKs. How do they get us faster SNARKs? Well, this is what lookups outside in other fields of computer science are good for. So you just look up the resultant of operation instead of actually computing it. So instead of representing something with constraints, for example, we can just pre-generate our table of operations, and then we're good to go. So that's what they're good for. One example, OK, so one example in that sense is take the XOR table. Here, for the case of 4-bit, this is our T from the slide before. Yeah? OK, so two desiderata we often want in lookups are some form of efficiency that they call super efficiency here. I'll talk about it. And the point of this talk, compatibility. All right. I'll introduce both of them. So super efficiency is very simple to understand. We do not want the prover to work linearly in the big table. So at proving time, I want the prover to work, yes, linearly in F, but I don't want it to run linearly in T. That's the thing. So I want it to be completely independent. Now, it's sort of counterintuitive. I'm going to prove a statement about the T. Can I even do this? Yes, you can. The important thing is that, OK, I'll tell this in a second. The important thing is that you preprocess, you need to work in that N at some point. So you need to preprocess stuff, store it, and use that auxiliary information later. So, of course, when do you care about this? Well, for example, when F is substantially smaller than N, which depends on the application, of course. All right. So if that makes sense, so it's not trivial to obtain super efficiency. It's not trivial that you need it either all the time, but it's not all constructions have it. So here's a list of constructions which do have super efficiency in this sense: CQ, CQ plus, which is just an improvement on CQ, lasso, which achieves that type of efficiency only on tables with a specific structure. So I don't have the technical definition fresh in my mind now, but basically you can decompose the algebraic representation of those tables in a nice way. Caulk plus, Baloo, and Lookup. And so other deployed proof systems also don't have it, but still useful. OK, so that's the first desideratum. The second desideratum, I'm going to call it compatibility, and it has to do with how we use lookup arguments with other proof systems. OK, so you may remember earlier I mentioned these two applications, right? So I'm going to use the faster SNARK application as an example, but everything I'm going to say here also holds for the other setting. So we want to achieve faster SNARKs for some computation. OK, that's our computation. It does a bunch of amazing things. And then if we want to use lookups, we can sort of split it into two blobs. The first blob that I call the general purpose blob, so it can be arithmetized by what we usually use for arithmetization, R1CS, arithmetic circuits, and such. And the second blob, the lookup blob, which is going to be lookupish. So as examples of the two, the top part is going to be represented by R1CS of some type, and the second part is going to be maybe a bunch of XORs or whatever. Yeah. Okay, once you do that, what do you need to do to prove the computation in a fast way? So you have you want the best of both worlds. Use your general purpose SNARKs for the first part, use your lookup SNARK argument for the other one. Are we done? Not quite. There is that bleeding wound over there, which is the shared state between these two things. So it's a computation, it's doing something, and you're going to have wires. Of course, they're not independent. You need to interface them. You cannot use these as two black boxes and never make them talk. So, but they need to be able to talk, and there's a bunch of ways to implement this. And some ways are nice, so they're going to link to each other nicely. Some ways are going to be less nice, less intuitive. I mean, you can still do that, but it's going to be more costly. So let's open the box of compatibility. What do we mean here in actual proof systems, right? What we mean is that the two proof systems need to have some, well, you can call it commit and prove compatibility of sorts. So both of the proof systems are going to use polynomial commitments, right? We saw that in the last talk. We know them as a basic building block as SNARKs. They need to be compatible. So what do I mean? Let's think, how do we use polynomial commitments in SNARKs? So in SNARKs, some SNARKs often, the first thing you do, you take an encoding of the witness and you commit to it, okay? This encoding is a polynomial. And then in lookups, what you do something similar. The first thing you do, you commit to an encoding of your f, the thing you're looking up in T. All right, so there are different types of encodings and different types of commitments, right? So on the top, you can see the Lagrange encoding with Lagrange interpolation for univariate polynomials. But then a bunch of proof systems use the hypercube as represented below. This leads to different encodings, different polynomials, different polynomial commitments, which are going to be the two handles over there. You want them, hopefully, to be the same type so you can make them talk efficiently. So this is what I mean by native compatibility. It's not a technical definition, but if the committed polynomials are of the same type and over the same field. All right. So let's see examples of compatibility and incompatibility in this proof system. So, for example, Plonk works pretty well with a bunch of those, for examples. And if you read the HyperPlonk paper, it's nicely modularly structured. So there is HyperPlonk, which is the proof system for our 1CS proper. And then HyperPlonk Plus, which is HyperPlonk, which is able to talk with an additional module, which is the sorry, that was a mistake. Which is a variant of Lookup for multivariate. So that's one case in which you need to modify the lookup argument to make it talk. And then, of course, trivial examples of incompatibility, take the bottom left and take the top right over there. OK. So if that makes sense, you could ask, fine, can't I use the two modules there anyway? So what happens if they're incompatible? Are we doomed? Of course not. They're not. You can do something. You can apply a SNARK on top of the shared wound and do everything. But this is less simple. This is the point of this whole thing. You are free to do that, but then you get way more complex in your system. It's less efficient. You need to modify APIs, interfaces, and maybe security properties too. You need to be cautious. And of course, maybe you're losing efficiency. So we want to save in those two dimensions. All right, so what are we trying to do here? We're trying to look at lookup arguments with both of these desiderata. And so, for example, why do we care? Because if you take, why do we care about proof systems such as HyperPlonk that are multivariate based? They have linear complexity, for example. And if you care about HyperPlonk, you may want to use it. So now the proof system that's used in the HyperPlonk paper is this modified Lookup I mentioned, which is not super efficient. So the only super efficient lookup I'm familiar with, please come to me if you know others, that is multivariate based is, for example, the lasso lookup. But lasso is super efficient only for specific type of tables. So what we want to construct is a proof system that's super efficient for any type of table and is natively compatible with this, yeah? And so once you have this, you can, plug it into proof systems like the one before, HyperPlonk, Spartan, and just do that. But there are others. Cool, so what are the constructions I want to talk about? So the first construction is a direct construction. It's called MeSeq. you hopefully get the reference. And it's a direct construction whose techniques are based on CQ. And it's modular, so you can plug it in. You can plug in any multilinear polynomial commitment scheme them, and it's going to work as your handle interface. So the second construction is actually a compiler. So the first question you could ask yourself when you saw my slide from before, so you want these two handles to be compatible, fine. We have these other lookup arguments that are univariate and nice. Can't you just transform all these cool systems into another? Well, actually, there are a bunch of simple techniques to do that. Some of them have different trade-offs, and the general compiler we propose is one of these systems. And I'm going to show you more about the compiler, but what does the compiler do? It takes in input a super efficient lookup argument with univariate polynomial commitment as interface, takes a multivariate polynomial commitment with very simple property, needs to be on the same field, and it gives you a super efficient lookup argument with multivariate polynomial commitment, so black box. Okay, and there are no fireworks there. You're going to see how it works. You're going to nod and say, okay, that makes sense, hopefully. And yeah, you can instantiate that with whatever you want. So right, so you can instantiate that on your favorite lookup systems with univariate features. I'm not going to talk so much about the efficiency of this second construction, but in general, it's sort of as efficient as MISIC, but since it works black box, it does more stuff. It doesn't look very well at what you're doing. So if you, probably you're going to be better off using the first one in many cases. Yeah. Okay, so some numbers. If you care, look at the rest of the table, but I will focus just on the last two rows. So the last row is our work. And then you can see lasso from structure tables. We're going to talk about lasso and structure tables later more. But so what would I want to take from this? The fact that the prover does linear job in group operation and field operations. And you can have a rough idea that I have concrete constants here for our proof systems. I don't know the concrete constants for lasso. I don't know if they're easy to extrapolate either. So if you want numbers, for example, say you're doing a lookup of around 1,000, your proof is around a few kilobytes. How much does it grow? If you increase that, it doesn't grow much. So those logarithms act as they tend to do logarithms. Sure, so some technical intuitions. I'm going to give a very, very superficial perspective on the first construction. And they're sort of, most of the techniques of MISIC are techniques of CQ. I'm just going to mention the usual suspects. So the univariate sum check lemma from Aurora, the lookup lemma, and cache quotient. If you've never seen this, I'm not hoping it's going to make sense to you now. But if you've seen it, you're just going to recognize it. The cache quotient techniques from CQ. So how do you use these guys? I mean, also these are usual suspect you would expect. You put them with the sum check protocol. Now, CQ as it is, you cannot quite transform it directly. But if you look at CQ as AHP or polynomial AHP, you can sort of see this transformation sort of easily. And we care, that's MISIC, basically. Instead, I want to talk about the compiler, which I have some hopes of bringing to get in touch with. All right. So what's the compiler trying to do? The compiler is trying to get a univariate polynomial commitment, a lookup argument with that type of interface, and a multivariate polynomial commitment, and give me that. So I want to achieve a proof system where the interface of my verifier is some encoding of this f over here of that form. So me is referring to the multivariate case. Nice. So that's the interface of my verifier. The verifier holds this. Just got it from the prover. In brackets, I just mean the commitment to that. Also have some other shapes to make the relation clear. So those are the same. Those are the same. Fine. So what's the first thing that the prover can do? The prover can use the building block over there. So I can use a lookup argument for univariate polynomials. Sure. So the prover can send the proof for univariate lookup, but with respect to what polynomial? So I need to send the polynomial first. So it sends another commitment to f. It's a vector. As it encodes it with Lagrange interpolation as a univariate polynomial, it sends it. It's sort of done. The job is done except, so yes, that's the same. So what's left is this very simple property that we need to show. We must show that those two commitments refer to the same vector. OK, so what do these commitments look like? They are brackets, so they commit to these two polynomials, respectively. Yeah. So hypercube on top and Lagrange on the bottom. What do? We do, we're going to do a sum check of sort. So we just sample a random point, sigma, and then I'm going to use I take a random evaluation in the point of the univariate polynomial. And now I'm going to link it to something else. So you can see that if you open the box of F univariate, if you look at the second row, that's what it looks like. And so it's basically a linear combination of the type. So it's the Fi points and the lambda de Lagrange polynomials in sigma. That's it. So I have a commitment to F. That's the top row, a commitment in the multivariate thing. I just need, if I have a commitment to the second thing, to the lambda in sigma, I'm done. So let's have it. P commits to it with the multivariate thing. And then it needs to show it as the right shape. That's all that's left. And we do, now this is the moment that all intuitions are sort of going to be compressed here. It proves that it's actually the right shape. You can see it here roughly. We're using the H is, this is a multilinear encoding of my domain for the univariate polynomials. This is a run, then you can see challenges over here and here, and so on and so forth. So we're just checking that linear product over there in the right form. And this is the compiler. This is it. So run a sum check on that. You're done. I shouldn't have done that. But this is it. OK, so what should you bring home about whether this stuff is useful or not? Is it useful all the time? Well, so remember the first, I don't know if I have a picture here. I do, I think. So let's talk about SNARK architecture. I will submit to you that this is useful if you want a simple architecture, but other architectures are possible. So earlier I showed you this diagram, right? So if you're comfortable, for whatever reason, doing this is useful to you, maybe you should use this. But there are probably more performance-proof systems out there that have a different architecture. So this is one thing you could do. So take an actual architecture, bring everything into lookups. Don't do the R1CS versus something else, or general versus lookups. Just bring everything into the lookup spectrum, and that's what you get. And maybe that's better. But it's a more complex system, maybe. So that's the first caveat. Second caveat, types of tables where this is useful. So I said that you may remember this slide. And you can notice that the second row here is for unstructured tables for lasso. What happens to lasso for structured tables? So structured tables, lasso is pretty efficient. And in practice, it is. I don't know how they perform, but I expect for many tables of that form, lasso proving time could be better. So probably MISIC is better for unstructured tables, which means plausibly, for example, very unstructured tables are permission lists I was mentioning before, so arbitrary sets of sorts. This is just a miscellaneous point about how do you think of MISIC. So think of it as a modular version of CQ that you can instantiate with various multilinear polynomial commitments. So also remember, the compiler I showed you is one among a spectrum of others. Other compilers are possible, and they have different caveats, different SRSs, different trade-offs. So this is not the only way to do this. Wrapping up, so two constructions for super efficient lookups compatible with multivariate proof systems. We saw two concrete construction and the compiler. What's next? So one thing you could ask, can you put zero knowledge here? Yes. One possibility is probably extending some zero-knowledge techniques for CQ from this recent paper at PKC. Then we're working on implementation, and last but not first, ePrint. Thank you.
Thank you, Matteo. Any questions? Don't be shy. Yay. Wait 1 second for the mic. Gotta get the sound on the video.
So these are revenge on my last question, I guess.
What sort of pre-processing do you need to do? Because I saw some pre-processing in the table.
Right. So there's this, I forget what it looks like exactly, but you just pre-compute all possible, here's one KZG for all possible points that you care about. This is one of the things you do in the pre-processing. So Feist-Kravatovich and such, for example. That's one of the fundamental steps, but it depends on the proof system. Thank you.
Thank you very much, Matteo.